Alright, so today we are starting Unit 2, and we are starting the section on the derivative and talking about how the derivative comes back to the concept of the tangent line problem.
Is this the x delta x?
So, when we talk about the derivative, it all comes back to four major concepts. So the four principles of calculus that were all developed back in the 17th century are the tangent line problem, which we're going to talk about in this section, velocity and acceleration, and how those relate to calculus. We will talk about that in section 2. The concept of using calculus to find minimum and maximum. So you'll see calculus used a lot when they're trying to find maximum yields and things like that in crops. They have someone run a calculus analysis on some data to see where that comes from, and then the area, using calculus to find maximum and minimum areas as well. We'll get to that when we talk about optimization in chapter 4. There are four main people that are known as the fathers of calculus. Isaac Newton. Isaac Newton is very well known. He's considered, obviously he created the laws of gravitational motion, but he's also considered the father of calculus. His concepts of gravity and stuff like that were extremely influential in the development of what we now call calculus. The next one is Rene Descartes. Rene Descartes, it's in pre-calc you learn what's called Descartes' rule that helps you to find positive and negative solutions. He also has very important parts within calculus. One of the other main people is Gottfried Leibniz. We'll talk later about the Leibniz rule or the Leibniz theory. When it comes to calculus, he's also very, very popular within that. And then the last one is Pierre de Fermat. And these are all mostly French. As you can tell, Descartes, Leibniz, and Fermat are all French. So this was very popular work. Like we said, most of these people were dead before 1700. So this is all very, very old work. But calculus is where basically is the development of everything that we now currently call basic algebra. So, I don't want to dive too much more into that. So, the tangent line problem. So, the whole basis of calculus comes back to this. So, we know how to find slope of lines. Right? But we don't know how to find slope of anything bigger than lines. So like quadratics, we don't know how to find the slope of a quadratic. It's not possible. Okay? Circles, we don't know how to find the slope of that. Okay? This go up, this go down. And basically any polynomial that is not lines, we don't know how to find slope of. And that really bothered Isaac Newton. And so he started to look at the way things moved. Like he would take a wheel and see, okay, why are certain wheels more effective than other wheels on certain vehicles? And he was trying to find the mathematical reason for that. Well, so it all comes back to this concept of a tangent line. So when you're finding the slope of something, what you're really finding is the slope of a tangent line that intersects at that specific point. So whenever we find a derivative in calculus, what you were doing is you were finding an equation to help you find the slope of a line passing through your graph at a specific point. And I know that's probably like, okay, that doesn't really make sense. But really what you're doing, so let's say I wanted to find the slope here, slope of this line at, let's say this is x equals 2. Well, we would take the derivative of that equation, we would plug in the 0.2, and that would give me the slope of that line when x equals 2.
That seems easy.
Okay? So, it all comes back to the question, okay, so if I have a line, how do I know how to find the derivative? Well, that's what we're going to talk about. So, when it comes to secant lines, in algebra, how do you find slope of a secant line? How do you find slope in algebra?
Rise over run.
Rise over run. What's another way?
What you like?
y2 minus y1 over x2 minus x1. Yep, or you can use point slope form. Yep.
Count the spaces.
Count spaces. Say what? Technically, yeah, you can use Pythagorean theorem. Yeah, technically. But that only works if you're on a grid. But yeah, that would work as well. Okay. Okay, so that's how you find it algebraically. But now, we're not working with just lines. We're working with secant lines. And a secant line is, again, you're finding 2 points on a line that's curved and finding its slope. So it's not as simple as y2 minus y1 over x2 minus x1 anymore. So what we do is we pick 2 points on that line. Okay? So if I have a curve, I pick 2 points and I want to find the slope of this secant line. I find those 2 points where my secant line crosses through that line. Okay? I call the first equation, or the first point, C f of c. Okay? The first point is C f of c. And the second point is C plus delta x and f of c plus delta x. So basically what that's saying, what does delta x mean? Change in x. I don't know what that change in x is, because I don't know exactly where that line crosses. But I know I know what c is. C is a number. I don't know what c plus delta x is. That's where calculus comes in. I can mathematically calculate the change in x to help me figure out what that delta x is. So now if I plug into my slope equation, I have f of c plus delta x minus, that's y2, y1, f of c all over x2, c plus delta x minus x1, c. So then I look at this, well, can I cancel any of that? The only thing that cancels are the c's on the bottom. So, how do I find slope in calculus? F of c plus delta x minus f of c over delta x. And again, you've seen that formula before. We did it in the P chapter. We did it in chapter 1 with limits, with infinite limits. Like I said, it would come back around, and I wanted you to be comfortable at least understanding what it's talking about. So when I teach you this, it's not completely new. This here is referred to as the difference quotient. That is referred to as the difference quotient. This formula. Okay? And the reason it's called the difference quotient is it's taking the difference of 2 points, y values, and dividing it by the difference of their x values. So we can't call it slope because it's not really slope, but it's about as close as we can get, mathematically speaking, to finding slope of curves.
That would have to be a constant curve, right?
Correct.
If it's going up and down, it wouldn't.
Now, a curve may have a million different slopes. you're finding slope at a particular point, depending on what that curve does.
So if you want the 2 points.
Right, so you're finding, if I draw a line through 2 points, and I'm finding that slope, that's what I'm doing by doing the.
So you're finding the slope of the line in between the 2 points.
Mhm.
Okay.
Yep.
So if you were to put in the ends, would you have the slope of the line?
Yep. Yep.
So you couldn't find slope, just the whole curve?
Nope.
It would have to be between 2 points?
So slope of a curve, if I was to say find the slope of this curve, you can't. You can find the slope at points on that curve, but not of an entire curve. Because if you look at, just to give you an example of why you can't do that,
Is it just because it's infinite?
right, there's infinitely many slopes.
Okay.
So if I look at a parabola, and I ask you to find the slope of that parabola, well, the slope here is approximately 0. It's flat, right? The slope here is positive. The slope here is negative. And each independent point you pick along that curve is going to have a slightly different slope. There's not going to be a single 2 points. I shouldn't say that. Normally, there is not multiple points on a curve that have the same slope. Most of them are going to have different slopes depending on where you are at on the curve. Okay. All right. I spent more time on that than I wanted to, but that's okay. So, definition of a tangent line with slope m. If f is defined on the open interval c, and the limit as delta x approaches 0 of change in y over change in x, because that's really what slope is, right? Change in y over change in x. y2 minus y1 over x2 minus x1. You're finding a delta y over delta x. Is what we just talked about. The limit as delta x approaches 0 of f of c plus delta x minus f of c over delta x. That is the slope of my tangent line at that point.
So that's what we just talked about.
Yes. Okay? Then the line passing through that point, c f of c, is the tangent line to the graph at c f of c. So basically what it's saying is whatever arbitrary point you pick to find the slope at, you are finding the slope of a line that crosses through that point on the graph. And tangent, again, meaning only passes through the graph at that exact point, nowhere else. Okay? All right. So, let's actually do it. So, we have a line, 2x minus 3. I want to know, what is the slope when c equals 2? Well, the nice thing about lines, you already know how to find slope of lines, right? How do I find slope of a line? Just m. So in this case, what do I know the slope is? 2. Okay? And does it matter what x value I choose with a line? The slope is always going to be 2. So that's why I always start teaching this concept with lines, because it's something you already know the slope of. So that way you have an arbitrary value that you know what it looks like to look back on. And again, it's the limit as delta x approaches 0 of f of c plus delta x minus f of c all over delta x. That is the limit we have to find. So, as we talked about back in chapter 1 and in the P chapter, where do I start? What do I need to find first to do this problem? You plug your 2 in for C, 100% right. So this becomes f of 2 plus delta x minus f of 2 all over delta x. Okay? Does everyone see why we plugged in 2? Right
You
there.
need those apps?
Huh?
Why
Yes.
You do.
That's saying the function. Now what do I need to do? Not quite. I need to find f of 2 plus delta x. So I now got to start finding what is this.
Let's just cancel the delta x's.
You can't, because of the plus and the minus. So you've got to first find f of 2 plus delta x. How do I do that? No. Everywhere I see an x in f of x, what do I put in? 2 plus delta x. So, how many x's are there in f of x? Just one. So this becomes 2 times 2 plus delta x minus 3.
Is this still all supposed to be in that first box up here?
So we're plugging that bottom one into the 2x minus 3.
Yep.
Okay. Do we do that for each one?
So I'm taking this value, plugging it in for x up there.
Okay. For each term.
This is just like substitution, right?
It's just like substitution. So now I got to find f of 2. So how do I find f of 2? Plug 2 in for x, right? 2 times 2 minus 3. Well, that one I can actually find an answer for. 2 times 2 is 4, minus 3 is 1. Everybody with me so far?
Why did you need to do both of them in both ways?
I'm doing the whole top.
Okay.
Because it's f of 2 plus delta x minus f
So
of
you'll
2.
end up putting the what's in red minus 1.
Yes.
So then the bottom, are we doing the bottom on this?
So the bottom, we're just going to leave as delta x. You never do anything with the bottom.
Okay.
Well, right now, you don't do anything with it.
So I left it the delta x there in the red.
Yep.
You get 1 or the delta x down.
Where? Here?
Yeah.
All I did was plug this in
Yep.
for x up here.
Okay, so what do you do on the bottom?
All I did was take 2.
How'd you go from the right red to the bottom green?
They're 2 separate things.
Okay.
They're both parts of that.
They're both-
Put in the f of 2, right?
Yeah, that's what I did here. F of 2. So this is part 1 of the top.
Yep.
This is part 2 of the top.
So you just plug.
I just did each one separately.
Okay, you plug them into each individually.
Yep.
Okay.
But
We'll get to this chapter.
Yes, we will. I just haven't done it yet. So if I plug in what I have, f of 2 plus delta x is 2 times 2 plus delta x minus 3 minus f of 2, which is 1, all over delta x. Now to Josh's question, do I need to simplify this first part? Now I do.
You distribute.
So now I distribute. 2 times 2 is 4, plus 2 times delta x is 2 delta x. Negative 3 minus 1 is negative 4.
One of those cancel.
And again, if you've done this correctly, everything that does not have a delta x should cancel.
You're gonna get 2. Right?
So the 4 and the 4 cancel.
You get delta x.
So I've got 2 delta x over delta x. And then the delta x's cancel. So my answer is just 2. What did we say the slope of the line should be?
2.
2? What was it? 2.
check this. So
Now, if this was not linear, at this point you would still have a c left. Like if this was a quadratic, you would have c left. Then you would have to plug in that specific c value to find that answer.
Get back onto the very top.
Oh, no, check that. Sorry, we plugged in up here, so you won't have a c. Retract my previous statement.
But when given something like that, can we just look at it and say slope is 2?
Nope,
Okay, so
you gotta work through the process. Because I give you linear examples, so you have something that's tangible for you to do. So you can practice that concept before we move on to harder concepts.
Okay. And why can we cancel delta x's at the end?
Here? because there's no addition or subtraction. We got rid of all addition and subtraction, so all that's left here is multiply and divide. At that point, you can cancel if there's no add or subtract. But if there's add or subtract in the problem, you can't cancel. We good? Does that make sense? Ish. For the most part.
Yeah. That was not bad.
All right. Now, we want to find the slope of our tangent line at those two specific points. Okay? We want to find the slope of the tangent line at those two specific points. Okay? So, we can't just plug in a C value right away. Reason being, if I plug in 0 for C right away, I then have to go back through and redo the whole process again, putting in -1. So in this case, we're going to leave it as C when we plug in. We're just going to put C in for X.
What's it asking you to find?
It's wanting us to find the slope at those 2 points.
And that's your equation for that.
Yep, and this is the f of x we're trying to find the slope of.
Why don't you just plug in and find slope?
Okay,
You can't do your.
It's a curve.
I thought.
Because it's
I
curved.
would do that.
it's curved, so you can't. So, what we have to do is we have to find the limit as delta x approaches 0 of f of c plus delta x minus f of c all over delta x.
So that's just the original.
That's the original theorem. That's the equation for a tangent line. Yes. Now, in this case, though, we are going to leave the c's. We're not going to substitute anything in for the c's till the very end. Yes. Delta x is just a change in. C is a point that you're given on a line. So the first thing we need to do is we need to find f of c plus delta x. So we're going to take c plus delta x and plug it in everywhere we see x in our original equation, x squared plus 1. So we're going to have c plus delta x squared plus 1.
Oh, no, we get the foil.
Now we have to FOIL.
Why?
I love it.
You're a liar.
Don't do it yet.
So that's over nothing.
Not yet.
Oh,
We're just doing, all we're doing is this first
Got it.
part, f of c plus delta x. I always break it up into chunks, otherwise it gets to be too much.
So since it's the same thing now, can we like it won't be a full foil. will it?
It will be a full FOIL, yeah. Because remember, this is c plus delta x times c plus delta x. So c times, if we do our FOIL here, c times c is c squared. C times delta x is c delta x. Delta x times c is also c delta x. Delta x times delta x is delta x squared. And then that plus 1 comes along for the ride.
So the delta squared.
That's actually good.
Okay? So, we now need to combine like terms. Well, how many like terms are there in here?
One.
Just the one in the middle, right? So I've got c squared plus, how many c delta x's do I have? 2. So 2c delta x plus delta x squared plus 1. That is f of c plus delta x.
That's just the one.
That's just the one term.
Hi all.
Yeah, then we have to have the minus of
Oh,
c.
Grace is tweaking over there.
Oh boy.
Now, minus.
We're just leaving it at c though.
Now, f of c. So, what that means, everywhere I see x, I'm going to replace x with c. So this becomes c squared plus 1. That is f of c. Just replace x with c. And that's all over delta x.
And then,
So, factor something out. Yes.
yeah, oh, okay.
Now I have to try and cancel. So I got to see, okay, what can I cancel? Well, c squared minus c squared. Those are gone. Then you got 1 minus 1, also gone.
Gone.
So if you've done this right, every term left should have delta x in it.
Yes.
So I've got 2c delta x plus delta x squared all over delta x. Now we got to see, okay, how can I simplify this to get rid of delta x on the bottom? Well, what does the top have in common? So I factor out of delta x. So I have delta x times 2c plus delta x all over delta x.
Wait, so it's, you have two c delta x, so shouldn't it be plus c delta x? There's still one left when you factor one more.
Yeah.
No, because you're getting rid of one.
Because I've got 2c delta x, so it's 2c times delta x.
That's all one term though, isn't it? Two c
Right,
delta
but those are two different variables, so they're multiplied together, so I can just pull them out.
So can we cross out the
So either one you can take.
X. Oh.
Delta X.
And then
So
this
it's c
delta
times
x is from delta x times delta x.
It's c times delta x, not
Yes.
c delta x as one term.
So when you're
Yes.
factoring, you're just rearranging them.
Yep. I'm just pulling out what they have in common to rearrange. Yep. Now I'm going to cancel delta x on top and bottom.
This looks familiar.
I get asked the question all the time, why can't we just cancel delta x here? Technically you are, but if you don't do the step and pull out what they have in common, you're going to lose this delta x. You're just going to cross it out willy-nilly and get rid of it. Okay? Plus, it then gives you the idea, anytime I have something in common on top and bottom, I can start just willy-nilly crossing stuff out. And you have to factor it out before you can cross it out. So now I've got the limit as delta x approaches 0
That's the question.
of 2c plus delta x.
Why can't we put them, squish them back together? Be solid.
Because you want them separate.
Because of the sign.
Now I plug in 2c plus 0. So the answer I get is 2c. That is the general formula to find slope at a point C.
Use direct substitute.
Yep, and now if I want to find the slope at 0, 1, was C my x value or my y value up here? X. So what do you think I need to plug in from up there? The x. So at 0, 1, I want to know the slope. I put 0 in for slope, or for C. So at 0, 1, what's the slope of x squared plus 1? 0. Do the same thing with negative 1, 2. What's the slope at negative 1? It is negative 2. So I'm finding specific points on my graph and finding their slope at that specific point.
Seems like there's gotta be an easier way to get to two c.
There is. I'm just not
That's a
teaching
long
it
way
to you.
Oh,
Okay, I got lost somewhere after the green.
All right. Okay, again, I am recording this. So,
Yeah, I got buried.
so you factor out delta x.
Yep, got it,
You cancel the delta x's out.
got it.
That's true. Now you've got the limit process way up here. The limit is delta x approaches 0. I now have to plug that 0 in to get rid of that spare delta x.
It's just direct.
Okay.
Direct sub 2c plus 0 is 2c.
Okay.
Then I got to go back to the problem, which wanted me to find the slope of my line at those 2 points. You plug those x values back in, and that gives me the slope at 0 and the slope at negative 1.
Are you always going to plug in the x values?
Yes, always will plug in the x values.
That's what I was.
So the y values are just, they're there just to try and they have no points on that.
Just like a minute.
Oh, there's.
Any questions on that process? Now do you see why I made sure to talk about doing this a couple times before we get there? Because otherwise, today would have been way over your heads more than it may already be.
Okay, go for it.
Okay? So, if you have a vertical tangent line, then your slope is undefined. The reason when we say it has undefined slope is because the limit as delta x approaches 0 is either infinity or negative infinity. And as we've already discussed, we can't find infinite limits. So that is why when we say a vertical line has undefined slope, that's why. Because its slope is technically either positive infinity or negative infinity. And we don't know which one it is. We can't find limits at infinity. That's why when we teach you that in algebra, that it's undefined, that's why it is. That's why divide by 0 gives you an error on a calculator, because it's technically an infinite limit.
Oh, it's.
That's why it's undefined. It's an infinite limit. We just don't teach you that until calculus.
I never thought about that.
What's up? Okay? So, a derivative, just to kind of tie this back in here. Derivative, if I ask you to find a derivative, and you have all this written down, so we'll just talk through this slide and then we'll be done for today. If I ask you to find a derivative, or I say to differentiate, what I'm asking you to do is the limit process. C plus delta x minus f of c over delta x. Okay? The definition of a derivative, how it's written in a calculus book, is the definition of x, of f at x is f prime of x. So you're going to see me write derivatives from now on as f prime. Okay? F prime of x means derivative is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. Only if the limit exists. So if the limit does not exist, well then it's an infinite slope. The slope does not exist. You can write derivatives in lots of different ways. F prime of x means derivative. dy dx means derivative. Y prime means derivative. D over dx of f of x means derivative. Dx of y means derivative.
It's written in all those ways.
It's written in all these different ways because all these different ways have different contexts. Okay? So tomorrow, well, I can talk about this quick too. dy dx is equal to, stands for the derivative of y with respect to x. So if it's dy over dt, derivative of y with respect to time. So when Mr. Drowley taught you derivatives, and you were doing them with acceleration and velocity, you were doing dy over dt, derivative of y with respect to time. Yeah. Okay. Let's see. Yep, we'll pick up with the cubic example tomorrow.
What does the derivative do for the